Hi, welcome back to College Algebra. This is week 7. We'll talk about how to multiply and factor polynomials. We'll cover 4.3, 4.5, and 4.6. And here are the list of measurable outcomes. Okay, let's talk about how to multiply polynomials. In the last lecture, we talked about how to add and subtract polynomials. And in this case, we talk about how to multiply polynomials. And this is essentially using the law of exponents that we saw in the last lecture. So if I want to multiply two monomials, then I multiply the coefficient, and then I add the powers of all the exponents that have the same base. So 7 times 3 times 5 is 15, and then x squared times x cubed. You add the exponent to get x to the 5th. Y to the 7 times y. You add the exponent to get y to the 8. Then we might to multiply polynomials, then we have to use the law of the distributive property of multiplication. And so 5y cubed, you multiply into, so this term is multiplied into each of these terms. So 5y cubed times 2y squared, that's 10y to the 5th. And then 5y cubed times negative 7y, give you negative 35y to the 4th. Again, we add the exponent. And 5y cubed times 6, we get a 30y cubed. Same thing here, we take each of the term here, distribute into this term, this times this, and then this times that, and then combine them. Okay, so but what do we have for more than one term for each of the operand that we're multiplying? So for example, what if you have a binomial times a binomial? And then basically what that means is that we have to take each of the term in the first and multiply by each of the term in the second. So x times x, x times 5, 3 times x, 3 times 5. So every term has to multiply to each other, and we combine like terms. So when we combine like terms, x squared here, 5x plus 3x is 8x, and then 15. So for example, you have this is a binomial on the left, and then a trinomial on the right. So that means each of the term on the left here, the two terms, have to multiply by each of the 3 terms here. So we should have 6 terms total, and then combine it like terms after that. So for example, 2x squared, you have to multiply each of that into the second term, and then the 4 have to be multiplied by each of the terms of the trinomial. So if I do that, we get 6 terms here, and when we combine like terms, we get something like that. So please look over this, the lecture notes when I post them. Okay, another way to do this, you might remember this from algebra in high school, is when you have a binomial times a binomial here, we use something called FOIL, which is first, outer, inner, last. The first term is 3y times 7y. The outer terms is these two outer terms right here, and the inner terms are the two inner terms right here. Then the last is this one and this one are the last terms. So that's how we usually try to multiply two binomials, and then combine like terms at the end. Some special cases for difference of squares and perfect squared trinomials. Notice when I multiply, notice these terms, especially in the sense that 2x plus 3, 2x minus 3, they're the same except for this one is plus, this one's minus. And when we have something like this, the middle terms will cancel. So notice that the outer and the outer term 2x times negative 3 is negative 6x, and the inner terms 3 times 2x is positive 6x. Those will cancel. So this will happen when we have this special case. And another special case is when you have something is being squared, a binomial is being squared. So in this case, the middle term will be the same, and they get double, because 3x times 7 is 21x, 7 times 3x is 21x. So this would be double to get 42x. And so here's a summary. If you have a plus b and a minus b, again, everything's the same except for a plus and a minus. Then the middle term will cancel, and all we have is the first terms, a times a is a squared, and the last term, b times negative b is negative b squared. And then the other case is when you have a plus b squared or a minus b squared. Again, the middle term is just get double, so a times b twice is 2ab, a times negative b twice is negative 2ab. So you want to kind of make sure we understand these special cases and be able to do it quickly. So for example, this is a case of a difference of squares, where again the middle term will cancel because of the minus and the plus. So we have a 36 c squared, and then the last term is minus 49d squared, because the two middle terms here will cancel. And then this is the case where you have a perfect square trinomial, and so that means that we have to so square this, square that, and then the middle term will get double. So for example, this is being squared to get 25x squared. The middle 5x times negative 2 is being double to get negative 20x, and then the last term is being squared. So again, the middle term is the first term times the last term, and then we double it because of minus, and then this is a negative because of the negative here. Same thing here, the first term is being squared, the last term is being squared here, and then these two terms right here, you get multiplied and then you double it. When you have something to the cube, you just gotta do it slowly. So that means it's x plus y squared times x plus y, because you multiply it 3 times. And so this is the special case we saw earlier. So x plus y squared is x squared plus 2xy plus y squared, and then when you multiply this, we have to do what we saw earlier, where we have to multiply each of the 3 terms here by each of the term on this side. And so we got 6 term total. This is about translating between the algebraic form and English form. So when I say square of sum of x and y, that means the sum of x and y is being squared. When I say the sum of the squares of x and y, that means you x squared and then y squared, and then we add them. And then the square of the product of 3 and x means 3 times x squared. And let's do an application here. So this is actually a very useful application. Suppose you have a piece of cardboard like this, and we want to cut up the corners, the 4 corners, and then fold them up into a box. And so suppose that I decide to when we cut up the corners, it have to be the same amount. So let's call that x. And then the question is, let's find out the volume of the resulting box. So if I have a piece of cardboard and we want to make a box, cutting x on each corner, what's the new volume of this new box? So notice that if I take out x here, let's say this is 20 by 20. So if I take out x from each, then this length right here would be 20, or this length 20 minus 2x, because I'm this is 20, subtracting x here means I'm subtracting 2x. So when I fold it up, notice I have the base of the box is 20 minus 2x by 20 minus 2x, because that's the base here. And the height is x, because that's what we're folding up. And so to get the volume, we this base times length times width times height. So the length is 20 minus x, the width is 20 minus x, the height is x. If I multiply this out, again I distribute, this is 20 minus x minus 2x squared. So if I use that trick I saw earlier with squaring, again 20 squared minus 2x squared is 4x squared, and then minus 2x times 20 double is negative 80x. And then finally distribute this x, will give you this term. And so notice this is a polynomial that represent the volume of the box, where x is how much we cut out. And so if I take a piece of paper and I cut out x, then this function represents the volume of the new box as a function of x, as a function of how much I cut out. Yeah, in calculus we actually will see this. If you ever move on to calculus, one of the questions is that if you have a cardboard like this and we want to know how much should I cut, what is the value of x should I cut, so that the box is the biggest possible box in terms of volume, right? And so that's one of the application that we can solve in calculus, where we want to maximize the volume of a box, and the question is how much do I cut to make sure that my new box is has maximum volume. And if I were to cut, say 4, and I plug in 4 into the function, then that means that the volume will have the volume of the box is the resultant value. So again, this is a function of the volume of the new box, where the input is how much I'm going to cut from the corners. Okay, let's talk about how to factor. So we're going to factor by greatest common factor and factoring by grouping. Okay, so what does that mean, a factor? Factor means that we want to write a certain expression into a product of two smaller units. So for example, this 35 is a factor. We factor 35 into 5 and 7. We can factor this term, trinomial, into a product of two binomial, for example. So 5 and 7 are factors of 35. 2x plus 1 and x minus 6 are factors of this polynomial. So the greatest common factor, we want to pull out a factor that is in common for all of them, and we want to pull out the greatest so that we can simplify our expression. So for example, 9, 18, and 6, the greatest common factor is going to be a 3, and then x to the 4, x cubed, and x squared. The greatest common factor is x squared, because x squared is in all of these terms, and it is the most you can get, so it's the greatest. 3 is in each of these, and 3 is the most you can get out of these constants. So together, 3x squared is the greatest common factor. We want to pull it out from our polynomial. So again, factoring is making things smaller so we can see it better. And so let's factor out by a factor on the greatest common factor. So between the 12 and 30, the greatest common factor is, well, let's look at the constant first. The greatest common constant is 6. 6 is a factor of 12 and 30 and is the biggest for both. And then x cubed and x squared, the greatest common factor is x squared. So 6x squared is the GCF, or greatest common factor. We can write this as basically, if I take out 6x squared, what I have left is 2x. And if I multiply this back, I get this again. So taking out 6x squared into each of these out of each of these terms, now I can pull this out by using the distributive property in reverse. Notice the 6x squared is a common factor now, and so I want to pull that outside of both, and then that's how I can factor out the greatest common factor. Notice if I multiply back in, I get the original again. Same thing here. Notice 3 is a common factor of the constants, and then CD, right, is the greatest common factor of the other terms. So if I pull out that out of all of the terms, then what I have left is this. Again, you always want to check by multiplying it again to make sure that you get the original term again. Okay, pull out the greatest common factor here. Well, x plus 2, x plus 2, x plus 2 means all these is certainly is a factor of all of them. And then x cubed, x, and 9, there's nothing in common there, so x plus 2 is the greatest common factor. So if I pull that out, pull out that all the terms, and what I have left is x cubed, x, and 9. And that's how you can pull out x plus 2. Factoring by grouping. So when we multiply two binomial, we multiply this by each of these, and then you have to do it again, this by each of these. And so factoring by grouping is basically reversing this. So if I start out with the bottom, how can I factor it back into the top? And so we basically have to look at these first two terms, factor the common factor, look at these, factor the common factor, and then reverse that process. So this is called factoring by grouping. So we identify, when we factor, we always first have to find the GCF of everything and pull that out. That will simplify a lot of our work. And then after that, we have to find the GCF of each of the first pair of terms and also the second pair of terms. And then hoping once we do that, we find a common factor that we can pull out at the end. So let's see some examples. So again, usually this has 4 terms. Look at the first 2 terms, find the GCF of it. And look at the second 2 terms, find the GCF of that, and then pull it out, and hoping there's some kind of a common factor we can pull out again at the end. So again, notice in all these terms there's no GCF, so we don't pull anything out of the entire thing. So let's look at the individual one. So look at the first 2 terms. What's the GCF of this? Well, between 6 and 21, that's going to be a 3, and then there's an A here and A here, so the GCF of this is 3A. So I pull that out of this to get this. And then for this one, the GCF is a 2, so I pull that out. And now this is the next step. If I haven't done that, if I notice that there's something in common in both of these, 2b minus 7, 2b minus 7 is common, so I pull that out of both to pull it out, and then what I have left is 3a and a 2 over here. Now, this only factor by grouping only works if once I divide up into two parts and I do the GCF of both, and I get something that is in common. If I don't have something that's in common here, then this process doesn't work. Let's see another example. So again, there's nothing in common for all four. So let's break this up into the first two terms and the last two terms. And so the GCF of this is x squared. GCF of this is -3. So pull those out. And notice again, I have something in common. X plus 3, x plus 3. I pull that out of both to get and then what I have left is x squared and then -3. So again, this only works if having done this, I have something in common here. So same thing here, but the difference here is that notice I have something. There's a GCF of all four, so I always want to pull. If there's GCF of all four, I need to pull that out first. So that GCF is 3pq. So I pull that out of everything to make this simpler. And now I apply grouping to these four terms right here. So I have put these two terms here, and then put these two terms here, and again find the GCF. There's a 2p I can pull out here, and there's a 5 I can pull out here. And again, this works because now these terms are the same. I pull that out of both, and then that's how I factor by grouping. Now, it's possible. So the question is, how do we know to pull out the first two terms and the last two terms? Well, that doesn't always work. So for example, if I try to do that with this one, so I again try to do the first two terms and last two terms, I notice if I do that, notice the terms here. So the GCF here is 2, GCF here is -1, and notice these two terms are not the same. So that means that for grouping,